And we're going to go on to our final talk of the session today by Ramaswamy Balasubramaniam.
Thank you very much. My name is Balasubramaniam. I go by the name Bala to people who don't know me. My talk is on scaling of liquefaction systems and the effects of gravity. My co-authors are Ali Koshani, who's from NASA Ames Research Center, and Ryan Groton-Rath and Wesley Johnson from NASA Glenn Research Center. Next slide, please. Yes, our objective here is to analyze the sensitivity of the G level, be it on Earth, Mars, or Moon, on liquefaction of oxygen for ISRU applications. Sensitivity or lack thereof would be important for ground testing of these technologies and validating them. Next slide, please. So for background, there was a recent study completed by a multi-center NASA team. They performed a state study on various liquefaction technologies. At that time, they were looking at the Mars ascent vehicle and the descent module. The assumptions were that oxygen is being produced at a rate of about 2.2 kilograms per hour, which corresponds to...
Bala, we have a request that you're a little hard to hear from quietness. Could you speak into the mic or turn up your volume to help folks who are having trouble?
Okay, can you hear me better?
Thank you. Thank you very much.
Okay, so the 2.2 kilogram per second heat removal rate corresponds to about 250 watts of cooling power. And they looked at mass, power, and reliability as the metrics for the down select. Next slide, please. The technologies traded were listed here. I won't go through each of them. The Lin cycle is a popular one on the ground that's to produce large-scale liquefaction. The other technologies looked at were liquefaction outside of the tank before it is pumped into the storage tank, liquefaction inside the tank by some kind of a finned heat exchanger, and liquefaction on the tube, on the tank surfaces, either inside the tank or outside the tank. And the down select was made to pursue the tube on tank option, basically cooling tubes mounted outside the tank. Next slide, please. So here is a depiction of the tube on tank technology, which is also called the broad area cooling. To the right of the figure, you see the tank. On the surface of which, on the outside, are mounted these cooling tubes. The cooling tubes, in this case, circulate cold neon. The neon itself is cooled by coupling to a cryo cooler. The cryo cooler has a lift capability, which is the heat extraction capability from the tank of about 150 to 200 watts, though the cryo cooler itself takes 10 times the amount of power. So we want to cool the tank on the outside, pump the oxygen into the tank, and thereby liquefy it. Next slide, please. Here is a prototype test hardware that is being assembled here at NASA Glenn. To the left, you see the tank made of aluminum. It is about 2 meters tall. Diameter is a little more than a meter, close to 1.25 meters. The tank wall is about a centimeter thick in aluminum. In the middle picture, you see it insulated from the outside by MLI insulation, and it's being prepped by hanging on a lid that will then be mounted inside a thermal vacuum changer for testing. Two rounds of tests are being anticipated. One with the industrial cryo cooler that's shown on the right. That test is supposed to be starting very soon, end of this year, early next year, following which the cryo cooler that is being designed for the lunar purposes will be tested along with this tank. Next slide, please. Okay, for the sake of analysis here, I'm going to simplify the tank geometry to be perfectly cylindrical with a flat lid. The cooling flow of neon flows from the top through these several cooling tubes on the sides of the tank. I'm going to assume that the tank pressure is constant, and I've depicted rather magnified view of the condensate film that forms on the side of the tank and drains and collects at the bottom. Next slide, please. Okay, so what are the effects of gravity on this problem? Gravity affects the condensate film drainage. The film thickness increases and drainage is slower as G is reduced. You can have natural convection in the superheated vapor if the vapor is indeed superheated. Natural convection produces a significant flow and mixing, and that flow is somewhat slower as G is reduced. G also affects the liquid vapor interface. In true microgravity, where the bond number is very low, the interface shape is significantly affected. But in partial gravity, Moon, Mars, the bond number can be shown to be very large in these tanks, and the interface shape is similar to that on Earth. In addition, you have some hydrostatic pressure effects, but they can be shown to be small. For a full tank, the hydrostatic pressure compared to the tank pressure is about 20% or so, and in partial gravity is even lower. Next slide, please. So in the assumptions, in the analysis, the following assumptions are made: that it is at quasi-steady state, so time enters only parametrically via the amount of liquid in the bottom portion of the tank. We assume that the tank pressure is constant. We assume that the film condensation is laminar, and you have a Nusselt type film condensation on the vertical surfaces, the cylindrical surface. On the top lid, which is also cooled by the incoming neon, we use the model of Gerstmann and Griffith, which is a dripping condensation model underneath the tank lid. We will not take into account any condensation on the liquid pool surface. And we assume that the flow of neon in the coolant tubes is turbulent. We neglect any contact resistance between those tubes and the tank wall. And it can also be shown that gravity has a negligible effect. The so-called Richardson number, which compares gravity to the convection inside the tube, is small, 10% or so in 1G, and smaller yet for partial G. Next slide, please. So in the calculations, I'm going to use the standard heat transfer coefficients for the Nusselt condensation film as expanded upon by Sparrow and coworkers to include other effects. I also used the Gerstmann and Griffith dripping model, the heat transfer coefficient that they have calculated, and standard correlations for the coolant flow in the tube. Next slide, please. Now, to estimate the condensation heat transfer coefficients, I'm going to assume that across the condensate film, there's like a 1 degree temperature drop. And if you use that in the heat transfer expressions that I presented before, you get the heat transfer coefficient in the thousands, watt per meter squared Kelvin, and somewhat decreases as the G is reduced. And in the cooling tube itself, the turbulent flow computations are not affected by gravity. And immediately from these calculations or estimations, one can see that the condensation heat transfer is on the order of tens of kilowatts. So the condensation heat transfer coefficient multiplied by the areas, surface areas involved, multiplied by the assumed 1 degree temperature drop over the condensate film gives 24 kilowatts in 1G, 15 kilowatts in 16G. And those are all way above the cooling capacity available from the cryocooler, which is on the order of 150 to 200 watts. So we can immediately conclude that the temperature drop in the condensate film is much less than 1 Kelvin. Another conclusion you can immediately draw from this is that liquefaction in these applications is limited by the cooling capacity of the cryocooler and not by any condensate film behavior and dynamics. Next slide, please. So those are estimates. I'm going to do some calculations now. I write down the energy balance for the neon flow. The neon flow picks up heat from the tube wall. The tube wall itself picks up heat from the condensation that's occurring on the inside of the tank. I put in typical parameters, 8 cooling tubes, each cooling tube carrying 2 grams per second of neon flow rate. Tube sizes of ½ inch diameter, and tank sizes that I mentioned before, about 2 meters in height and a meter and a quarter diameter. I'm also going to assume that the neon comes in at a temperature of 80 Kelvin. Next slide, please. And so we can see from these calculations that the wall temperature stays pretty close to the saturation temperature. The neon warms up from 80 to about the saturation temperature. The 2 black dashed lines shown are at the edge of the lid, and then all the way from the lid to the bottom of the tank. We see that the temperature drop over the film is really in the order of millikelvins, and that the film thickness is on the order of tens of microns. The cooling capacity is about 176 or so watts for zero fill, which decreases somewhat with fill level at 100%. Next slide, please. I won't go through this in detail, but Minkowitz and Sparrow studied this problem and see what are the things that contribute to increasing heat transfer and decreasing heat transfer coefficients. The top 3, basically natural convection, vapor cooling, and any liquid subcooling, tends to increase the heat transfer coefficient and therefore diminish the influence of condensate film and gravity on the cooling capacity. Interfacial resistance has a slight effect in decreasing the heat transfer coefficient, and non-condensables, if any, that are present can have a significant impact. These are yet to be studied for the particular parameters of oxygen condensation, but it is expected that the heat transfer coefficients for condensation will still dominate that of the flow in the neon tubes. Next slide, please, and this is my final slide. So for this tube-on-tank liquefaction, I conclude that liquefaction is limited by the cryocooler capability. And for gravity levels on Earth, Moon, on Mars, the condensation film has practically no influence on the rate of heat transfer. Non-condensables might have an effect on liquefaction that need to be studied or calculated. The theory does exist, but it needs to be calculated. And I conclude that testing in 1G is likely adequate for validating the hardware. That's the end of my talk. If there's any time, I can take any questions. If not, I will see the chat.
Yeah, all right. Thank you.